Nati, and I'm from Medical Doctor International Studies. I'm going to be teaching you physics, and this is the first presentation. So let's start. Actually, this presentation regards more the mathematical stuff you need to know. It's not really physics, it's more math, and it's really important to know these things and to really listen carefully, because it's the basics for being able to solve physics problems. So we're going to be talking about units, and then we're going to be talking about vector and scalar quantities. And let's start with the overview. Regarding the units, we're going to be talking about the SI unit system, which is very common, about scaling units, and about unit conversion. Talking about vectors, we're going to talk about definitions, we're going to talk about vector algebra, and talk about coordinate systems. Maybe it sounds odd and, I don't know, maybe complicated to you, these names, but actually you're going to be doctors, so you're going to bump into much more difficult and much more long names. So everything is going to be really explained, I hope. And let's start. So at the SI base unit, you know that in physics we work with a large variety of units, but these units and these numbers and these quantities need to go into formulas and solve problems. This is why we can't use whatever we want, we can't use any unit we want for physical quantity, and we use the SI unit system. The SI unit system includes three really important sizes. The first size represents the length of something. The unit representing length in the SI unit system is meters. So we have meter, the unit symbol for it is M. We have the mass in kilograms, the symbol is kg, and the time is represented in seconds, as you probably know, and the seconds are symboled with the letter S. We have other stuff that I'm not going to talk about. We're going to know them more closely when we continue and get to know the stuff we need to know. But for instance, you have here mole. Mole is one quantity of amount of substance. It's used more commonly in chemistry. And we have amperes for electric current, etc. Okay, so let's see what we can do with this. Actually, if we look at physical quantities, and I would really want you in the end to use this link below and go to a website that really shows a lot of interesting interactive things about physics, well, you can understand that our world sometimes is very large, and when you talk about, for instance, planets and solar systems and galaxies and such big things, you sometimes have really large masses, really large distances, really large physical quantities. Sometimes when you talk about more smaller stuff, like in biology, when you talk about cells, when you talk about atoms and molecules, proteins, you talk about really small things. This is why we need to be able to scale things, and here you can see in the orange line that the base size for everything is just 1. We can have 1, 2, 3 of any stuff we want. Like if we talk about mass, we can have 1 kilogram, 2 kilogram, 3 kilogram. This is generally the base thing we use. But what happens if we have something really heavy? So let's say we have something that has a mass of 1,000,000 grams. Then instead of saying 1,000,000 grams, we might say that we have 1 megagram. So the words on the left here represent the different sizes in order to scale the units. If we have 1,000,000 of something, we can use the word mega. If we have 1,000 something, we can use the word kilo, etc. And here on the right, you can see the representation. If I want to see how much is 1 mega, 1 mega is 1 times 10 to the power of 6. 1 giga is 1 times 10 to the power of 9. And the larger it gets, and the larger is the power. And we have these words to represent these very commonly used sizes. But we can also, as I said, look at very small stuff, very light stuff, very short stuff in time, in length, in mass, and other things that we're going to talk about. So I guess you probably know that 100th of a meter is 1 centimeter. So here you can see centi is 100th of something, and it is actually 1 times 10 to the minus 2. You have also here something interesting, micro. If you're talking about micrometer or 1 micron, you are actually talking about something that has a length of 1 millionth of a meter. If you're talking about 1 nanometer, then you're talking about something which is as large as 1 billionth of a meter. And actually, when we talk about nanotechnology, this is actually a technology, whatever the technology is, regarding the sizes of 1 billionth of a meter. Also here you have 2 special scales which I wanted to point out. If you have 1,000 kilograms, you can give it a name, it's 1 ton. And if you have 10 to the minus 10 meters, only regarding length, of course, then 1 angstrom is equal to 10 to the minus 10 meters. I hope you understand what I mean. So actually, we have also SI derived units. I was talking about the SI base units, which are meters, grams, seconds, or maybe kilograms. So these were the base units talking about length, mass, time, but sometimes we have more complex units, but they are also built, derived from these basic blocks, which were the base units. Let me give you an example. If we're talking about something's speed, let's say something has a speed of 5 meters per second, it's not length and it's not time, it's a velocity. Or you could say it's speed. So the units of speed are meters per second. They are derived from the base SI units, and you can see examples here. Here are some examples. If you're talking about something that happens a few times every second, then the units are hertz. These are the units of frequency. If you're talking about force, a force is in the units of 1 Newton. Newton is actually 1 kilogram times meter divided by second squared, and we're going to talk about most of this stuff, so I don't want to really talk about this table too much, but I just want you to understand that units for many other stuff that we haven't talked about could be derived from the basic SI units and could be given new names. So we're going to bump into these things, but on a later occasion. Okay, so what happens if I want to convert units? What is the conversion method? Something I would really like you to adopt to yourself is this method. Let's say I have a speed of 15 kilometers per hour. What I do, the first thing is take these 15 kilometers per hour and multiply them with the conversion ratio. If I want to go from 15 kilometers per hour to the SI units, kilometers must be meters and hours must be seconds, because kilometers is not the basic length unit and hour is not the basic time unit. So 50 kilometers per hour, I would multiply with the conversion ratio of meter to kilometer, and you can see it here. Then if I use the denominator and the numerator as I'm supposed to, then the kilometer with the kilometer reduces, and later I can multiply also with the time. The time conversion ratio is that 1 hour is 3600 seconds. Then I would reduce all the unwanted numbers, all the unwanted unit quantities, and then I would get a new number and I would get the units that I want, and you can try it by yourself. It's 4.16 meters per second. It's the same size, but the number is different because we're not using the same units. So let's see a problem. we want to convert this mass to units of kilograms. The SI basic units are grams. So micrograms, as we see here, is not the basic unit, and kilograms is not the basic unit. What we would like to do is convert this mass to units of kilograms in the following way. 25 micrograms, I just write it, then I write the conversion ratio in order to get from 1 micro into just the base units. So 10 to the minus 6 is 1 micro. You can notice that I put micro in the denominator in order to get the micro here and the micro here reduced. Then I multiply by the ratio of 1 kilo is 1000, and then as I write the number, you can see that I have kilo in the numerator and have kilograms, and it's 2.5 to the power of 10. So I changed 25 micrograms into units of kilograms. It's still the same quantity, but it's written differently. Let's talk a little bit about vectors and scalars. So what are scalars actually? They are physical quantities which can be fully described only by magnitude, only by size. One numerical value and you have all you need. What is vectors? Vector quantities are physical quantities that are fully described by both a magnitude and a direction. If you want an example, when you play Angry Birds, you take the bird and you throw it, and you want the bird to hit the pigs. So when you throw the bird, you can actually see the velocities vector when you throw the bird. It can also be directed somewhere, and it can also get different magnitudes. This is why the bird's velocity is a vector. And let's see a little bit examples for scalars and vectors. We have scalars which are time, volume, pressure. If I talk about time, for instance, and I say that I have 10 minutes before the bus arrives, then 10 minutes is the magnitude of the time, but there is no direction. I can't say I have 10 minutes to the left or to the right. It's just 10 minutes. So this is a scalar quantity. And if I talk about vector quantities, there are a few things here that you don't know maybe, but you definitely know what a force is. I can exert a force on a certain object, but if I push a table, it's really important what is the direction of the push. So I can push the table upward, I can push it downwards, I can push it forward or to the back or to the right or to the left. So I can say I have a force of a specific magnitude, let's say 6 newtons, and there should also be a direction. Some definitions about vectors. If I want to talk about vector A and represent it, vector A must have a magnitude or a size, and it also has to have a direction. That's why if I want to represent a vector and draw it somehow, an arrow is great because an arrow has a size and it also has a magnitude. We use lowercase letters usually, and we put an arrow on top to just let people know that we're talking about a vector. If we want to talk about a different vector, vector B, but vector B is in the same direction and has the same magnitude, then actually vectors A and B are equal. A equals B. If we talk about a vector which is in the opposite direction but has still the same magnitude, then we are talking about opposite vectors, and C equals minus A. We can also talk about perpendicular vectors. Actually, the direction must be perpendicular. They don't have to be the same size, but they need to have an angle of 90 degrees between them. Then we can say the two vectors are perpendicular to each other. It's written here that the magnitude must be the same because